this. Let's go. Let's do this. Yeah. All right. Okay, so now we're gonna remove the surface, so to speak. By the way, here we ignored the minus sign. We just want to know the pressure. We don't care that on the surface it's pushing down. Pressure is generally considered, it's always positive, and it's the orientation of the surface that determines the direction. But pressure always pushes out on whatever you're applying it to. Like in the just like in the tension in a string, we don't consider it positive on one side of the string and negative on the other. It's just a number. And it always pulls. Tension always pulls, pressure always pushes. You can't push something with a string, and you can't pull something with pressure. Words to live by. So now we're going to remove the perfectly reflecting surface and replace it with a mathematical surface, just a surface, just a hypothetical surface in space, so to speak. So now remove the perfectly reflecting surface. Replace it with a mathematical surface. There ain't nothing there anymore. So now the incident photons continue past dA. Representing a flow of negative z momentum into it. While photons streaming through from the other side take on the role of the reflected photons. And notice that those represent a flow of positive z momentum out of the surface. So we've got negative z momentum flowing in and positive z momentum flowing out. We've got negative z momentum flowing into dA, positive z momentum flowing out of dA. is equivalent to negative momentum flowing in. What you're losing by momentum flowing out, you could just as well consider as a gain of negative momentum flowing in. And that's the key here. Which is equivalent to a negative flow into the air. So what we do then is we just integrate over all directions and remove the factor of 2, because that factor of 2 came from the reflection. And so that's gone now. And so now we just integrate over every. That's it. We remove the factor of 2 and just integrate over every direction, because there's no reflection happening anymore.
Because momentum now stays constant.
Yeah, so now
The cosine.
no photon is changing its momentum anymore, so we don't need that. We still have the cosine theta because we only want the z component, but we don't have the 2 because we're not talking about P final minus P initial.
Yeah.
Right, nothing, no photon had a momentum added to it.
It's simple subtraction.
Well, in a sense, what we're doing is that because negative flow in equals positive flow out, then when we add the negative momentum of this photon to the, well, put it like this. So this photon carries negative momentum through the surface. This photon carries positive momentum out of the surface. So we can think of what we're doing is we're adding the negative flow in here minus the negative flow in here to get the total momentum, basically. So, thus we can remove the leading factor to and extend the integration to over all solid angle. Extend the integration to over all solid angle. Because the net momentum transfer is the same. The net momentum transfer into the surface is the same for this as it is for that, is what we're arguing here. So we say that P rad lambda equals 1 over C integral of I lambda cosine squared theta d omega. And when we do the phi integral, we get 2 pi, and that's, so before we had 4 pi over c, but now it'll just be 2 pi over c because we don't have the factor of 2 anymore. Integral from -1 to 1, because now we're doing it over all theta, of I lambda u squared du. And it's always interesting to look at the special case of an isotropic radiation field and see what happens. So now if we consider I lambda to be constant, we just pull it out of the integral.
Then you need cube by 2.
So P rad lambda will just be, what am I going to say? Will be 2 pi over c I lambda integral from -1 to 1 mu squared d mu. So that's half mu squared. And if I plug in, sorry, it's third mu cubed is what I want to say, right? Third mu cubed, right? So this will be 2 pi over c I lambda times third mu cubed evaluated at 1 and -1. So then I'll get 1/3 minus 1/3, or 2/3, right? So then this becomes 4 pi over 3c I lambda after you do the integral. So as an aside, we do the same thing when we talk about gas pressure. In other words, you can look at it as, first you put a surface there that the molecules are bouncing off of. And then you're talking about the pressure on the walls of the container. But the gas pressure exists throughout the container. And there what you do is you say, okay, now I take out the wall and I say some particles are flowing down into the surface carrying negative z momentum into it. Others are flowing up through the surface carrying positive z momentum out of it. And so that's equivalent to negative z momentum going into it. And so in the gas 2, you can integrate over all directions after removing a factor of 2 to deduce what the gas pressure is. So even within the gas, we still talk about the pressure being the momentum transferred through a surface, an imaginary surface, per square meter per second. That's the pressure that it represents. And then if you put something physically there, the pressure results in a force on it. But if the pressure is the same on both sides, if the pressure if the pressure is the same on both sides, there's no net force because the pressure on one side is pushing this way, the pressure on the other side is pushing that way. Right. So it's important to understand that this is the pressure in the radiation field, but if you had something in there and that was the pressure on both sides of it, then it wouldn't have any net force on it. So to have a net radiation pressure force, the pressure has to be changing with distance. So that the pressure will be bigger on one side of the surface than the other side of the surface. That's when you have a net force. That's a general thing with pressure, is it's not pressure itself within a gas that causes forces on little portions of the gas. The pressure has to be varying with position within the gas so that there's more force set, like in the air in this room, for example. The pressure is diminishing with height. And that has to be true because then if I take a little cube of air in this room, then the pressure is higher on the bottom of it than it is on the top of it. So that means the air underneath the cube is pushing up harder than the air on top of it's pushing down. And that needs to be so because the cube has a weight. And so the net pressure force has to equal the gravitational force. And so that's why pressure decreases with height in the atmosphere, because you need to have pressure on the bottom of a layer being bigger than the pressure on the top to counteract the weight of the layer. That's true in Earth's atmosphere, it's true in the ocean, it's true in stars. We'll be using that later.
So pressure is given as a function of what do you call
That
it?
could be like radius from the center of
Radius,
the
yeah,
star, for example. Yeah.
Radial coordinate.
Yeah, so pressure will be a function of the radius within the star, and what we'll find is that the equation of hydrostatic equilibrium is that the derivative of the pressure is minus the density times the local acceleration due to gravity. And this is saying that the pressure force per unit volume is equal to the weight per unit volume. This is how that will be interpreted. Okay, go to black body radiation. That's always an interesting case too. For black body radiation, this says that P rad lambda is equal to 4 pi over 3c B lambda, because I lambda is B lambda for black body radiation. So now let's integrate overall wavelengths to find the total pressure. Integrating overall lambda, find the total radiation pressure P rad.
Is this the total radiation pressure for black body?
For black body radiation specifically,
Okay.
yes. We would always do that to find P rad. I'm saying now let's do it for black body radiation. The reason being is we know what B lambda is when we know what the integral B lambda over all wavelengths is. In general, we would have to know what I lambda was to do the integral over all wavelengths. But for B lambda, we do know what it is. We've got that specific formula for B lambda, the 2 pi hc cubed over lambda to the 5th, your mom times all that stuff, you know, right? So yields P rad for black body radiation, 4 pi over 3c integral from 0 to infinity of B lambda, but that integral is sigma t to the 4th power over pi. So that gives us 4 pi over 3c sigma t to the 4th power over pi. So then the pi's cancel, we just get 4 sigma over 3c t to the 4th power. But wait a minute, we said that the radiation energy density was 4 sigma over c t to the 4th power.
Oh, yeah.
So this is 1/3 of a t to the 4th, or a 4 sigma over c is the radiation constant. So this is 1/3 u. So for black body radiation, the pressure is 1/3 of the energy density. And note that pressure and energy density have the same units. It does work out because energy density is joules per cubic meter, right? But unit-wise, joules are force times distance, right? There's work units. So it's newtons per meter squared. So joules per cubic meter and newtons per meter squared are the same thing. They're equivalent. However, if you're expressing an energy density, you should say joules per meter cubed, because joules are energy and meter cubed is volume. And if you're expressing a pressure, you should say newtons per square meter. Even though they're equivalent to one another, you got to think about, well, what does this physically represent?
So if you multiply an extra meter.
Yeah, right. So if you put it in fundamental units, you know, kilograms, meters, and seconds, it looks the same. Dimensionally, it's the same thing, but it's better to think in terms of what's physically happening and call that joules per cubic meter if it's an energy density and force per newtons per square meter if it's a pressure. But that's why P can literally be 1/3 U. We don't need any unit corrections or anything like that. They have the same units, and so they can be a simple multiple of one another without being a contradiction. Yeah, and so this is an interesting result too, because it's different from the way a gas works, from an ideal gas. So contrast this. So let's write it out explicitly in words. Thus, the black body radiation pressure is 1/3 of the energy density. But for an ideal gas, the pressure is 2/3 of the energy density. Contrast this with a monatomic ideal gas. If it's diatomic, it changes a little bit. The ideal gas law says P is nKT, where N is the number density,
K is the Boltzmann and T is
and K is the Boltzmann constant, and T is the Kelvin temperature. And remember that in thermal equilibrium, each particle has the average particle kinetic energy is 3/2 kT.
Mm-hmm.
So therefore, the energy density in the gas is 3/2 nKT. The number density, number of particles per unit volume, times 3/2 kT, because that's their average energy. So if P is nKT and U is 3/2 nKT, it follows that P is 2/3 of U. Right? So that's an important difference. For radiation pressure, P is 1/3 of U, but for gas pressure, ideal gas pressure, P is 2/3 of U.
And if you add them up, the total pressures. Can you do that?
Sure, yeah, the total pressure is the sum of them, but you have to be careful because the U there is not the radiation energy density, it's the gas energy density. So in other words, it's well, it depends on which one you mean. So, just to be explicit, I'll call that U rad, okay, and I'll call this P gas, U gas. So P gas is 2/3 of the gas's kinetic energy density.
Okay.
Whereas for radiation pressure, P rad is 1/3 of the photon energy density. The energy density due to photons. So those are different things. We're comparing two different things. The gas's pressure is 2/3 of its energy density. The radiation's pressure is 1/3 of its energy density. And the total energy densities can be added, and so can the gas pressures, but they're not equal to one another. In general, U gas and U rad are different things. So you don't just get to there's no simple relation between the total pressure and the total energy density because of the fact that they're not the same as one another. But when you get to cosmology, this becomes very important because it turns out that the expansion of the universe, the equation that describes the expansion of the universe, contains both the pressure and the density. And the universe has both photons and matter in it, and they have different pressure relations to one another. And as we will see when we do more cosmology, when the universe was very young, it's the expansion of the universe that is stretching out the wavelengths of photons so that you get redshifts. When you see a distant galaxy, you may know that the light we see is redshifted. It's not caused by the motion of the galaxy away from us. It's caused by the expansion of space while the light was on its way to us.
I see.
That stretches out the wavelengths of photons. So if you run time backwards, then both the density of photons, most of the photons in the universe are cosmic background radiation photons. Turns out they vastly outnumber starlight, and the energy in them vastly outnumbers the total energy in starlight. So most of the energy density of radiation in the universe is due to the cosmic microwave background photons. Run the clock backwards towards the Big Bang. So the number of photons per unit volume gets bigger and bigger because you're shrinking the universe. Similarly, the number of particles, material particles per unit volume increases at the same rate. It's, because if you half the volume, then, if you make the universe half its present size, then any given cubic meter becomes an eighth of a cubic meter, because 1/2 times 1/2 is 1/8. And the number, roughly speaking, the number of particles, photons and material particles in that, on average, stays the same, so the density goes up by a factor of 8. So as you shrink the universe, by running the clock backwards, the energy in matter and the energy in radiation both increase, the energy densities do both increase because you're shrinking the universe, but the photon energy also, each individual photon's energy gets bigger because their wavelengths were shorter back then.
Yeah.
So there's an extra factor of increase in the photon's energies. And what that means is that early on, the universe most of the energy in the universe was in the form of radiation. But as the universe expanded, the radiation density, energy density, fell faster than the matter energy density, because not only did the density of photons decrease, but the individual photon energies also decreased as well.
Okay, so
And
they're lesser now than they used.
Yes, it's much less now than it used to be. Meanwhile, for the last 20 years, we've known that there appears to be a dark energy that, as far as we know, stays constant with time. It doesn't change. It's an energy associated with space-time itself. So as the universe expands, there's more and more dark energy. Energy conservation doesn't apply to the universe as a whole, it turns out. It does not. You get dark energy for free as the universe keeps expanding. And so
it's like a loophole.
It's a loophole, yeah. The energy conservation is a local thing. The total energy in the universe isn't conserved. Another way to realize that is, as the universe is expanding, the photons' wavelengths are increasing, so their energy is decreasing. And if you're wondering, like, well, where does that energy go? As far as we know, it doesn't go anywhere. It's just gone. So energy isn't conserved. It's just being lost, and it's not being converted into any other form.
Wow.
Yeah. So, have you had mechanics yet?
No.
Okay, so the reason for that is it turns out that for energy to be conserved, what's called the Hamiltonian of a system has to not depend on the time. And that's not the case for the universe as a whole. And so energy conservation doesn't apply as a result of that. So strangely enough, there's energy conservation seems like such a fundamental law. It's not, it turns out. It's only under the right conditions that energy is conserved. And in most closed, isolated systems, those conditions hold. But the universe as a whole doesn't satisfy it. And so energy as a whole in the universe is actually not conserved. The energy in the black body radiation the energy in the background radiation is diminishing with time, but dark energy is growing bigger and bigger. And so now we are in the so-called dark energy era, where the primary contribution to the energy density of the universe is in the form of dark energy. Early on, radiation energy density was the most important. Then there was the so-called matter era, when the radiation energy density fell below the matter energy density because it was falling faster because of the photons losing energy. Material particles don't lose energy as the universe expands, but photons do. Massless particles do lose energy as the universe expands, whereas massive particles always have their rest energy that never goes away. And so we used to think there was a radiation era and then a matter era, and then we discovered dark energy, and now we realize, no, there's 3 eras, and we're actually living in the dark energy era now, as best we know, assuming our understanding of dark energy is reasonably correct. The universe is now dominated by dark energy, which is why the expansion of the universe is speeding up instead of slowing down, because dark energy acts as a sort of negative gravity. It acts kind of like anti-gravity and causes the expansion of the universe to speed up rather than slowing down.
Oh, so it's accelerated.
So the universe's expansion is accelerating because of dark energy. Early on, it was slowing down before dark energy dominated things.
Oh, wow.
But over time, dark energy stays, the dark energy density stays constant while the radiation and matter densities fall with time. And so first radiation dominated, then matter dominated. So the universe was about 9 billion years old. And then after that, dark energy started dominating. And that was 5 billion years ago. So we've, for billions of years now, been in the dark energy era of the cosmos.
But this would also imply that dark energy was present before.
It was. But when the universe was smaller, there was less of it.
Okay.
Yeah, there was less of it. The amount of dark energy in any given cubic meter we think is constant, okay?
Okay, that's
so imagine a small region of space-time early on in the history of the universe. It's maybe it's a meter across, a cubic meter, okay? As the universe expands, then there's more and more dark energy in that co-moving volume because it's got more and more cubic meters in it. The radiation and matter energy, the total matter energy in it stays essentially constant because it still has the same number of particles in it. But the matter energy density overall is falling, the density, because that same amount of energy in the form of matter has been spread into a larger volume. So the energy per unit volume per cubic meter has decreased. The radiation energy in that co-moving volume has diminished because the photons are being redshifted by the expansion of the universe. So in a co-moving volume, a volume which is expanding, the total dark energy in that volume is constantly increasing. The total matter density, the total matter energy in that volume is staying constant, and the radiation energy is diminishing. So if you run things backwards, what you find is that early on the radiation density dominated, but the expansion of the universe is diluting it faster than it's diluting the matter energy density. And the dark energy is like whatever, it just stays constant. Every cubic meter that is being created, so to speak, has dark energy in it. And apparently it just comes for free. It's an intrinsic property of space-time, and so it just comes for free. There's no limit, it just keeps being created.
Wow.
Yeah, it's weird. It's weird. That's why the current paradigm in cosmology is called lambda CDM, because lambda is the symbol for the dark energy. And this stands for cold dark matter, because, as we'll also see, dark matter is more abundant. Assuming we're interpreting the observations correctly, dark matter is much more abundant than baryonic matter.
Yeah, it's like 21%. It's 29 to.
Yeah, it's like something like, I think the latest was like 68% dark energy, like 20. It's not gonna add up. 5% baryonic matter, and the rest is cold dark matter. So there, it's adding up because your mind has to do the subtract. But it's roughly that. So lambda CDM means that the universe is dominated by lambda dark energy, followed by cold dark matter, and then there's baryonic matter.
Wow.
It's just not part of the acronym.
Oh,
So if you go to at the AAS meeting, if you go to cosmology talks, you're eventually going to hear lambda CDM, and that's what that means. That's what that refers to. That's a capital Greek lambda.
That's so cool.
Yeah.
Yeah, that's the symbol that Einstein had in his.
Yes,
earlier
that's why we
form
use
to
that, because that's what he used to symbolize his hypothetical.
expand.
Uh,
No, he tried to control.
he wanted the universe to not be expanding or contracting. His equation said the universe should either expand or contract, so he added the cosmological constant to counteract it. Now the problem is it's unstable, it turns out. In other words, you can get a solution where the universe is static, but on the other hand, it's like balancing a pen on its point. In other words, the slightest perturbation and it tips over. The slightest perturbation in a universe that has just enough cosmological constant to counteract any tendency to expand or contract. If any little region of it becomes denser or less dense, it starts to expand or contract, and it'll keep doing that. So it's actually not a viable solution because it's an unstable solution. Perturbations grow instead of shrinking. But, so because Einstein used, so that's why we say one possibility for lambda is that it is a cosmological constant. We don't know what would produce it, but like Einstein's postulate was that the energy density of the cosmological constant was literally constant and the same everywhere at all times. And so that's our first guess as to what the dark energy is. But it could also be increasing with time or decreasing with time. We don't know because we don't know what it is. And so you can also build models where, for example, it's increasing with time, and that leads to what is known as the big rip.
Yeah.
After a finite amount of time, the so-called scale factor becomes infinity, and everything breaks apart, and the universe has a finite lifespan because eventually everything becomes infinitely far apart, and even atoms and so forth are ripped apart. If it's decreasing with time, in principle, you could have a recollapse of the universe into a big crunch, right? So, so there's various possibilities. If it's decreasing with time and then could go negative, then it starts acting like gravity instead of anti-gravity, and it could cause the universe to eventually collapse back on itself. So, but that's all speculative because we don't know what the heck it is. But you can easily plug it into the equations. The equation that describes the expansion of the universe is remarkably simple in form. Deriving it is not simple, but the equation itself is very easy and it's not hard to find solutions to it. So, yeah, which is pretty fun. Yeah. Well, that was a bit of a diversion, but in other words, we went to, so I was talking about that. I probably should have talked about something else, but I didn't.